If you've ever flown by the window and spent the whole trip staring at the clouds below, there's a detail sitting just a few inches from your face that you probably never noticed. The glass is never a perfect rectangle, never has sharp corners, it's always rounded, almost an oval. Most passengers assume that's just a design choice, something engineers picked because it looks cleaner, only it isn't. That shape exists because, decades ago, an entire commercial airplane broke apart in mid-air, killing everyone on board, and investigators traced the failure back to a single 90-degree corner. Sounds like something out of a disaster movie, doesn't it? But it's real, it's documented in official accident reports, and it permanently changed how every commercial aircraft has been designed ever since. From here, you're going to find out exactly what happened, why it almost ended commercial jet travel before it really started, and why that rounded detail you never paid attention to is actually one of the most expensive lessons modern engineering has ever learned. If you like digging into the hidden reasons behind things we use every day without ever questioning them, hit like and subscribe. Every new episode looks into a detail that seems small but hides a massive story behind it. Our story starts in the early 1950s. Right when commercial flying was shifting from a luxury reserved for the few into something increasingly common, the British manufacturer de Havilland launched the Comet, the world's first commercial jet airliner. It flew higher and faster than any propeller plane of its time, and that was a revolution. To fly at that altitude, the cabin had to be pressurized because the air outside, more than 10,000 meters up, is too thin for a human being to breathe. That means every single flight puts the fuselage through a complete cycle of pressurization and depressurization. It expands slightly as the plane climbs and returns to its normal size as it descends, over and over, flight after flight, year after year. It's essentially the same principle as inflating and deflating a balloon, except with a rigid metal structure instead of latex. The Comet entered commercial service in 1952 and was an immediate point of national pride, but in less than 2 years, 3 aircraft of that same model disintegrated mid-flight, with no warning from the crew beforehand. In January 1954, a comet exploded over the Mediterranean Sea near Italy. A few months later, in April of that same year, another comet from the same fleet met the exact same fate in the same part of the world. 3 losses involving the exact same aircraft type within roughly 2 years, all with eerily similar circumstances, was enough to shake public confidence in jet travel itself. Newspapers ran headlines questioning whether jet aircraft were simply too risky for ordinary passengers, and some airlines that had ordered the Comet quietly started looking at other options. British authorities grounded the entire fleet immediately and launched one of the most thorough investigations in aviation history up to that point. The problem was that modern black boxes didn't exist yet. There was no detailed flight data recording like today, and the wreckage was scattered across the bottom of the sea, in pieces too small to tell the full story on their own. Royal Navy ships and divers spent weeks dragging the seabed near the crash sites, recovering fragment after fragment of twisted metal, piece by piece, in one of the largest underwater salvage operations ever attempted up to that point, just to give engineers something physical to examine. Even after collecting as much wreckage as humanly possible, the fragments alone didn't explain anything. There was no single broken part that obviously caused the disaster, no melted engine, no severed control cable, nothing that pointed to a clear villain. That's when investigators had an idea that sounded almost excessive at first, but turned out to be brilliant. They recovered a large portion of the fuselage from one of the crashed aircraft, reassembled the structure, and placed the entire thing inside a giant tank filled with water. The choice of water wasn't random. Unlike air, water doesn't compress, so it's possible to pressurize and depressurize a submerged structure over and over without the risk of a violent explosion if it fails. That allowed them to safely simulate thousands of flight cycles in just a few weeks, compressing years of real operation into a single controlled laboratory experiment. And that's exactly what the engineers did. They pressurized and depressurized the fuselage repeatedly, simulating flight after flight, waiting to see where the structure would give way first. The answer showed up faster than anyone expected. The first cracks began forming right at the corners of the windows, which at the time were almost square with straight edges and sharply defined angles. Every pressurization cycle generated mechanical stress on the structure, and that stress didn't spread evenly across the fuselage. It concentrated at the points with the sharpest angles, exactly the 4 corners of each square window. Over time, cycle after cycle, those small concentrations of stress produced microscopic cracks. Those cracks grew, slowly at first, until, after hundreds of cycles, a crack reached a critical size and the fuselage simply couldn't hold anymore. The result was catastrophic structural failure, with the aircraft breaking apart in midair within a fraction of a second with no perceivable warning to the crew until the very last instant. The physics behind it is simpler than it sounds. Think about a sheet of paper you want to tear. If you try to tear it right from the middle, it's difficult. The force spreads across the whole fiber of the paper. But if you make a small cut at the edge first, the paper tears with surprising ease, starting from that exact point. It's the same reason a paperclip eventually snaps if you bend it back and forth enough times at the exact same spot, even though a single bend wouldn't do anything at all. The damage doesn't come from one strong hit, it builds up quietly, repetition after repetition, until the material simply gives up. The sharp corners of those square windows worked exactly like that small initial cut. They created a stress concentration point that, repeated thousands of times over the operational life of the aircraft, became the inevitable starting point for a fracture. The solution engineers arrived at, after months of testing, was as simple as the cause of the problem. Eliminate the corners, replace the right angles with smooth curves with no point of stress concentration at all. When a force is applied to a curved surface, it spreads evenly around the entire circumference, with no single point taking on a disproportionate load. The rounded windows that became standard after this were never a design preference. They were a structural necessity based on pure physics. That principle is so solid that, even today, more than 70 years later, no commercial aircraft manufacturer has ever gone back to producing a window with sharp corners. Every pressurized aircraft flying today, whether it's a small private jet or a wide-body airliner carrying over 300 passengers, follows the exact same rule discovered inside that British water tank back in the 1950s. The damage to de Havilland's reputation, though, was permanent. While the Comet fleet sat grounded for years going through redesigns, American manufacturers Boeing and Douglas kept developing their own jet airliners, the 707 and the DC-8. And once those aircraft were ready, airlines around the world had already lost confidence in the British design and turned to the American alternatives instead. Some aviation historians argue that those two crashes, more than any single business decision, are the reason the center of commercial jet manufacturing shifted from Britain to the United States for the following half-century. Now, here come the two details that almost never get mentioned when people tell this story, and they're going to change the way you look at any airplane from now on. The first detail is that this rule doesn't only apply to windows. Every single opening in a pressurized aircraft's fuselage, from the main boarding door to the cargo compartments and the emergency exits, follows that exact same rounded corner principle. Aerospace engineers call this stress concentration management, and it's one of the very first things checked on any new aircraft design before a single prototype is ever built. If you look closely at any commercial airplane next time you're at an airport, you'll notice that absolutely no opening on the fuselage has a sharp corner. Not one. The second detail is about the very testing method that solved the mystery in the first place. Using water tanks for structural fatigue testing became standard practice across the aviation industry after the Comet case, and it's still used today, decades later, to test the full structural life of new aircraft models before they ever enter commercial service. Manufacturers like Boeing and Airbus still maintain entire facilities dedicated to submerging complete fuselages in water and simulating decades' worth of pressurization cycles in a matter of months, specifically to guarantee that no new model ever repeats the Comet's fate. In other words, the accident that nearly ended commercial jet travel at its very beginning also created the exact method that now guarantees the structural safety of practically every aircraft flying in the world today. The Comet investigation also gave rise to an entire philosophy in engineering known as fail-safe design. The idea that a structure should be built so that a single small crack or defect never leads to total catastrophic failure on its own. That philosophy didn't stay limited to aviation either. It eventually spread into how bridges, pipelines, and even spacecraft are designed and tested. To this day, the Comet case is taught in materials science and aerospace engineering courses around the world, usually as the textbook example of how a tiny, overlooked geometric detail can bring down an entire system if nobody accounts for repeated stress over time. There's one more technical detail that most people don't know about, regarding why modern windows aren't a perfect circle, but rather a slightly elongated oval. A circle would distribute stress even more evenly than an oval, but a vertically elongated oval makes better use of the available fuselage space, giving passengers a decent view without compromising structural integrity. It's a calculated balance between engineering and usability, refined over decades since that very first Comet. The answer to why airplane windows are never square doesn't fit into a simple sentence about aesthetics or visual comfort. It lives in the combination of a real tragedy that cost lives, an investigation that reinvented the way aircraft structures are tested, and a principle of physics so fundamental that it survives intact in even the most modern aircraft taking off today. Next time you sit by a window seat and rest your head against that rounded glass, you'll know that curve isn't there by accident. It's there because once a single sharp corner was enough to tear a plane apart in mid-air, and aerospace engineering never let that happen again. Thanks for watching all the way through.